This lecture video is going to cover how to calculate and interpret a confidence interval for a proportion. Now to do this, we're going to look at a previous example problem, and I'm going to show you through visualization how we go about constructing this confidence interval. This example is where we were trying to estimate the proportion of college students who are in a relationship. And so if we were to graph this out visually, we have an x variable, which is whether or not a student is in a relationship. And so we have a column for yes, they are, and another bar for no, they're not. And our goal is to try to estimate the proportion of students in a relationship. Proportion of yes. Now this is a mystery to us, right? We don't know this population proportion. So what we'll do is this. We'll take a sample. So in this case, we took a sample of 125 observations. Right? So all of those observations we took a sample from. And that yielded a sample proportion, p hat. And in this case, p hat turns out to be 47 over 125, which is about 0.376. And so down below, I'll write a little p hat, and this is where we will plot that sample proportion. Now our goal is to estimate the population proportion. What we saw before with the central limit theorem and the distribution of sample proportions is that the population proportion equals the mean of the distribution of sample proportion. Those two values are exactly the same. And we know if we take enough observations, the distribution of sample proportions will become normal. I'm going to draw a normal distribution here, and I'll label this as normal. Again, that's assuming our sample size is large enough, and we'll talk about that a little bit later on. What we'll know is that this center point, the mean of this distribution, equals our population proportion. Now we talked about the likelihood that our sample proportion falls exactly on that red vertical line. The mean is essentially 0. That likelihood is essentially a 0% chance our sample proportion is going to equal our exact population proportion or our mean of our sample proportions. It's essentially a 0% chance. So here's what we'll do. We know since our distribution is approximately normal, right? If we remember, I'll write a little z distribution, right? We know if we look at the mean and we go 2 standard deviations in each direction, 2 standard deviations in this direction, 2 sigma, and 2 standard deviations in this direction. We know according to our central limit theorem that about 95% of values fall within 2 standard deviations. So what we're going to do is this. We don't know where this starting point is, right? This starting point is a mystery to us. Our starting point, however, will be our sample proportion. What we're going to do is go 2 standard deviations in each direction from this point. 1, 2, 1, 2. And our hope is for this interval to capture that red line. That's what our hope is, to capture that red line. Now, what is a standard deviation? Well, if we remember our standard deviation, sigma p hat, equals pi times 1 minus pi over our sample size. But maybe you kind of saw the problem here is we don't know pi. That's a mystery to us. So what we're going to do is we're going to use a sample standard deviation, or a sample standard error we'll denote as SP hat. And this will equal essentially that exact same equation. Instead of pi, though, we'll use our sample proportion to estimate pi. So we're using a sample and a sample statistic to estimate a population parameter. So what we'll do is if we wanted to create a 95% confidence interval, we would go 2 standard deviations in each direction. So what that would look like is this. We would take our sample proportion and we want to go 2 standard deviations, plus and minus, 2 standard deviations, where 2 is representing 95%, 2 standard deviations in each direction. And our standard deviation is the function p hat times 1 minus p hat over our sample size. This is our confidence interval for a 95% confidence interval. We can be however confident we want to be. All we would have to change is the number of standard deviations in each direction that we want to go. Right? If we wanted to be 99.7% confident, well, we can go approximately 3 standard deviations in each direction. If we wanted to be 68% confident, we can go 1 standard deviation in each direction, and that represents being 68% confident. Let's go back to our notes to recap all this out. For a confidence interval, we talked about and saw a visualization of how to come up with the equation for a confidence interval. What we're going to do is we're going to take our best guess p hat, right? That's our best guess for the population proportion. Yes, it's true that essentially there's a 0% chance we're exactly right, but that's our best guess. Then what we'll do is we'll go a certain number of standard deviations in each direction. That's what representing z star. You can think of z star as a z-score. And technically there are 2 z-scores that we're working with. Z star is 2 values. It's the positive value and it's a negative value. So we're going to be calculating this equation twice. We're going to be taking our sample proportion and adding a certain number of standard deviations or standard errors, and taking our sample proportion and subtracting a certain number of standard deviations or standard errors. And lastly, our standard error is this quantity right here. This is our estimate for the population standard error, or the population standard deviation of the distribution of sample proportions. This formula is going to give us a confidence interval to estimate our population parameter, pi, or the population proportion. Now let's calculate out that confidence interval. If we wanted to construct a 95% confidence interval for the population proportion of college students in a relationship, well, here's how we would go about doing that. Right? We know since we're dealing with a 95% confidence interval, we can just use the z-star value too. Going plus or minus 2 standard deviations in each direction will give us 95%, or approximate 95%. So looking at this equation down here, we took our sample proportion p hat, which was 0.376. We added and subtracted 2 standard deviations, which was z-star. And then we're going to multiply that by the value of our standard error, or standard deviation of our sample proportions, S sub p hat. And if we were to do this equation out, we would end up with the interval 0.29 to 0.462. You can think of that as 29% to 46.2%. Now the big question for us now is how are we going to interpret that confidence interval? And there's a few ways for us to think about this. The first way, if we remember, was if we were to keep taking confidence intervals over and over and over again, 125 college students, 125 college students, and over, if we did that an infinite amount of times, 95% of those intervals would contain or capture the population proportion. But that's kind of a weird way to think about things. Let's think of things in terms of an individual confidence interval. What we can say is we're 95% confident that the interval between 0.29 to 0.462, or if you wanted to write this as a percentage, 29% to 46.2%, we're 95% confident that this interval is capturing the population proportion of college students who are in a relationship. Now, we are unsure of what that exact population proportion is. However, we're 95% confident that this interval is capturing it. This is doing a much better job of us saying something like, hey, our sample proportion was 0.376, and we're essentially 0% confident that our population proportion is that exact value. This interval now is allowing us to be 95% confident that we're capturing our population proportion. This is how we calculate a confidence interval, and this is how we should interpret it. One additional thing we need to think about, though, is while this math will always work to calculate a confidence interval, certain conditions need to be met. Let's look at this example to see what conditions need to be met and why it would be a problem if they weren't met. The first conditions that we'll look at are these three right here. N times p hat needs to be greater than or equal to 10. N times 1 minus p hat needs to be greater than or equal to 10. And third, n needs to be less than 10% of the population. If one of those three conditions are not met, so they all need to be met. If one of those conditions are not met, well, what's going to happen? This distribution will not be normal. Why is that a problem? Well, we're finding probabilities and percentages associated with a normal distribution. Right? When we go 2 standard deviations in each direction, we know there's 95% there because we're assuming it's normal. If one of those three conditions are not met, our distribution would not be normal. And we would not know how confident we are when we go a certain number of standard deviations. Our confidence level would be a mystery to us. The fourth condition that needs to be met is for us to have a random sample. One reason we need to have a random sample is so that we're adequately representing our population. Right? If we have a biased sample, we would not do a good job of representing our population. Thus, we would not do a good job of representing our parameter, pi, our population proportion. But technically what's happening, if we think about things in terms of this distribution, is this. Imagine instead we sampled, not a random sample of college students, but maybe there was a college club called, Club Heartbreak. And it was a college club made up of recent people who got out of a relationship. So someone went to that club and took a random sample of 125 people. Almost all those people would not be in a relationship. Maybe a couple were there to just look at the misery of others. I don't know. That's kind of messed up. But most people would not be in a relationship at that club. So what would happen is if we were to calculate the sample proportion of people in a relationship, most of them wouldn't. So our sample proportion would be really small. If we were to repeat this process over and over again, the next day we go to that club and we take another sample of 125 people. Again, we would have a small sample proportion. We do it again. Again, would we have a small sample proportion. If we did this over and over again, the distribution of our sample proportions may very well still be normal if conditions 1, 2, and 3 are met. However, what's going to happen is this mean is going to change. It's going to shift. Our distributions shift. These two values, pi and mu p hat, would not equal each other. If you have a biased sample, your population proportion and the mean of the distribution of your sample proportions would not equal each other. You're not estimating what you're actually after. This is why we need to have a random sample. So pi and mu p hat equal each other. When we estimate the mean of the distribution of sample proportions, it equals the population proportion in which we're interested in. Next, we'll talk about some confidence interval theory.